In the module for week 9, we start looking at the most important aspect of C++, which is object-oriented programming, in particular of the definition and use of classes. So let's look at what we are going to do in this introduction. We're going to look at how classes are defined. So similarly to variables, so classes are elements of the language that can be defined and effectively generalize the notion given by the basic data types. Basically are new data types that can be defined and manipulated by the programmer to give to offer advanced capability that are now part of the basic language. So we're going to look at examples, the use of objects, and then how we construct and extract elements of this. So classes are kind of the fundamental component that distinguish C++ from the original C language. Basically, it goes from, in C, there were at most what they would call structs, which is kind of very basic syntactic sugar, but without any advanced capability, versus using classes that allow a fairly sophisticated way of protecting part of the data model behind a particular type that is introduced. One can offer a specific API for external users. And for example, one could change the entire internal representation while the external set of methods, effectively the API, would be unchanged. So it's a very important abstraction, generalizes kind of similarly to numbers and other basic data types like a float. A float has operations like plus, minus, multiplication. Now, a float happen to be stored in a particular sequence of bytes that is handled directly by the hardware. But you can think about building higher precision floating point operators that maybe use 64 bytes or more, again, not bits, but bytes and more. And on top of the basic float, 32 bits and 64 bits, and putting them together and present the same set of operator. So that can be accomplished with the use of classes. So typically, in addition to being defined by the users, they have internal data to represent the information and methods, or in the case that I was talking about operators, methods to manipulate both internally and externally the representation of the information inside a class. And then effectively, so this would characterize the properties and the behavior of that type. For example, out of real numbers, you can create complex numbers by storing, say, two real numbers. One is the imaginary part, and one is the real part, and then defining on top all the proper operators. What are the advantages of using classes? In a way, they provide a better way to abstract new types that match the concept that are important in a particular context, right? So an example could be in a game, we have an explosion that could be a particular data type happening. they can make the programs more concise. More important, the analysis, the readability of the code would be much more intuitive, of course, if we do things right. And with the explicit use of all the proper restrictions, for example, protecting some variables, making so only certain methods accessible to external users and so on, that can actually also help capture errors much faster, so that we express through the language the expectation in terms of how that particular data type is being used. But more important at all is the concept of having a proper abstraction. Effectively, the set of methods that are available from a public is the appearance of the data type to the users. One can then build a quick implementation, make it practical use, and then what happens underneath that abstraction can change entirely and still be used in the same way. And so it's a very powerful way to expose an API while the implementation underneath can be changed in terms of either generalizing or increasing efficiency or things like that. So let's look at a very simple case of a class. So let's say we want to have the concept of a rectangle. So we define this class rectangle, and the body of the class is contained between these curly braces. And as data type inside, we have width and length of a rectangle, and we describe that under private. So this means this is our internal representation, but we don't want anybody outside of the person building the type itself to expose the internal representation. For example, the ints could become floats or doubles, depending on the need. Maybe one can store the area and the length instead of width and length, and the information became calculated and derived. And then we look at what I was called before the API, so the visible way of representing the class. So that is part of the public part. And so one is a function set that set the width and the length of the rectangle, and an integer returning a function return an integer that calculate the area of that rectangle. So it's very simple, but it starts giving you the sense of the separation between the internal representation, what's publicly visible, and how those things can be handled in general. So in the use of the rectangles, now rectangles becomes a valid data type as anything else. And so and one in a portion of the program, after including this class, one can declare a bunch of variables of type rectangle. Then we have, for example, an integer. And so here we can look at the similarity of declaring a variable of type rectangle or a variable of type integer. Basically, there is no difference. There is the variable and there is the type. So structurally, this is the general definition of a class. So you have the keyword class, the name. So that's the name that basically you define based on what you make, and you want to make it as intuitive as possible. The curly braces, then the permission label. So that could be either private or public. And then a set of elements, those could be variables or methods. And then another permission label, and those can be switching back and forth between private and public. And then more elements and so on. The And by the way, those can be happening multiple times, so you don't have to group all the private or public stuff together. So this is the header, the body, and so we see the match with the example we just gave. The name of the class is rectangle, the keyword is class. The permission labels are in this case private and public. And then the various members are variables and methods and functions that are part of the implementation of the class. So the elements inside can be any type, the obviously built-in type, like here we have integers, but those could be also other classes. So they don't have to be built-in, they can be user-defined. So with that could be a type of a different type that is a user-defined, does not need to be an integer. So there could be, the members can be static and non-static. This is a somewhat advanced feature. So most of the time we use non-static members. All the members here are not static. So static are the members that basically are part of all the instances of the class. So as probably intuition will say, when we declare here multiple instances of a rectangle, each of those instances has its own copy of width and length, so that every rectangle has its own dimensions. And so those are elements that are not static. But let's say that we wanted to have a counter that keep track of how many rectangles we have total. We could add a static integer of a count that initially say we set at 0. And every time we create a rectangle, that gets incremented by 1. And every time we destroy a rectangle, it gets decremented by 1. So that at any given time, we could query the data structure to see how many rectangles have been created during the execution of a program. So in this sense, they act as global variables, in the sense they're still encapsulated in the class, so they're not global in that sense, the scope, but they're shared by all the instances of that class. So here, let's say we do static int count, and then if so all those instances will share the same variable count. If any of those will modified count, all the other will see the same modified value. So you can see that, for example, one could do every time you do a set, you might increase the count, and then you will know in general how many times the shape of rectangles have been changed, for example. So there are different type of member functions. In general, those are divided in two types. One, those are the accessor functions. So those are functions that are typically used just to read the value stored in the data structure, and they implement other that actually perform actual operations. Like, for example, we saw before, the set function changes the shape. So that's not just an access operator. So the member functions are declared inside the body of the class. And then the definition can be either inside or outside. So this is similar to what we have seen for general functions. There is a potential separation between declaration and definition. So the declaration, again, is just expressing the signature, how many parameters does he have, what is the type of the parameter, what is the type of the value returned. That has to be inside of the class itself, but then the actual definition with the body could be either immediately inside or outside. Those can access both public and private members. And then we will see there are two ways of referring to that, through a dot and for an arrow. That depends on whether we use the class from a direct variables or through a pointer. So this is important, the fact that the member function access all the data, private and public, because then functions that are external to the class, so that are non-members, can only access public aspects of the class itself. So let's go back to our rectangle example. So in this case, for example, we start giving the implementation for the area function. In this case, this is what we will call an inline method, because we don't just have the declaration, we have the full body, the full definition of the function itself. So this is an inline. If we wanted to define a function outside, so then we have to express in this way what is the class is part of. So in this case, void rectangle colon set. So this means this is the method set of the class rectangle. Obviously, the signature has to match the one that's given inside the class. And then in this case here, we assign the value to the local variable. So class name, member, function name, and this gives the scope in which the function is defined. So in the if the variable R1 is of type rectangle, to access the function, the method set, we use the dot operator, so R1.set 5.8. But if RP is a pointer to a rectangle, then we use this arrow, which is really minus greater than. So RP arrow set. So those are two different ways to refer to a member function, either through the dot for a direct variable declaration, or through the arrow if it's a pointer to the class. So const member function, as we saw before, consts are used as a way to indicate to the compiler that certain elements are not meant to modified. This is true also for member functions. Now the semantic then it changes a little bit. That means if a function or a method is defined of type of const, that means that method is not meant to modify anything inside the class. So it's a kind of reading elements. Or in the previous case, we discussed access functions. And so you have the name, parameter list, and const, and that can be used inside or outside. So no modification in the members. So those are, again, it's part of the debugging. Then the compiler will help you immediately as soon as you declare a const. If inside you made anything that could modify things, you will get an error, and that will help you avoid lots of mistakes that normally, if you had to catch later during debugging through examples, that would be a long, tedious process. So for example, if we have a class time, like here, and then inside we want to have a representation in hours, minutes, and seconds, As a public, we want to have a function that simply writes the time. So clearly this function is not meant to modify. Then we can define this as a const function. So this is the declaration. And then here outside, it's the actual definition. So we have the type, scope, write, no parameter. It's a const function. And then here we can do a print statement, cout hours, column, minutes, column, second, new line, and that's it. So if you by mistake do means equal means plus one, the compiler will give you an error. So for the small cost of writing const, unfortunately humans tend to be very lazy, so they try to avoid doing those things. But as soon as you start systematically using const for methods that don't modify the value, are not meant to modify the value, there's a lot of mistakes that can be caught very early. So in this way, we want to have the general approach into, on one side, that we want to hide the information, so make it private, and then have a very careful selection of access functions that could be made public, they could be made private, and then the more advanced feature are the protected one. This is not particularly important immediately. We can get to that later. And so, as a practical example, so we will have a full class representing time. So the private part is basically the internal representation of time. In this case, we use 3 integer for hours, minutes, and seconds. And then the public facing part is a set of methods. We saw, for example, write. We make it const because it's not meant to modify anything. We have 2 constructors. So those are the functions that are called as declaration of a variable. So one without parameters and one with setting immediately a certain time. And then, for example, we have a function that increments time or a function that set time. Again, all the others, basically, other than write, are obviously are meant to modify the value of time, so are not defined as const. Conceptually, though, this is kind of the abstraction that we build. The external user interface has two way of creating time, a way of writing time, one to set and one to increment time. And the internal representation effectively is invisible to the user of this class, not to the programmer. And that help encapsulating the abstraction of the concept without exposing in the internal representation and running the risk of mistakes and modification that provide unexpected results.